Trunk group maintenance simulation model. Here you see a diagram which represents the histogram of a distribution, the distribution being that of the loss deviation of a trunk group. Here we are simulating a trunk group of 36 trunks. Each trunk individually takes a random walk, that is, its performance parameter changes by 1 unit up or down at random at every tick of the clock. As the clock ticks on, the entire distribution spreads out over time, much like a sandcastle being washed away by each wave of the ocean. At any time, there is always a worst trunk in the group, which will be represented by a red thermometer bar in the upper left-hand corner. At the same time, there is an overall dispersion to the distribution, represented by the second moment, or the chi-square statistic. Here you see the time evolution of the worst trunk in the group. The green trace represents the time evolution of the second moment, or the chi-square, and as you can see, it grows approximately linearly in time, in accordance with the well-known theory of the Wiener process. We have done no work to control the distribution in this simulation run. The magenta curves show the time evolution of the decay of the distribution, starting out from well peaked at the beginning and becoming ever flatter as time goes on. Now we'll run the simulation again, but this time we'll introduce a maintenance policy to control the spread of the distribution. Here, to speed up the simulation, we're using only 12 trunks in this trunk group, and we're going to do work at a uniform rate. The bottom trace and the bottom thermometer bar represents the rate at which trunks are being repaired, and as you can see, it's going up linearly. The result of this is that we achieve a steady state distribution with a steady state trace on the worst trunk in the group and a steady state trace on the measure of dispersion. Now we'll run the simulation again, but we'll change policies. On the worst trunk, we have previously shown a white mark, which is a conventional maintenance limit. In this portion of the simulation, we do work whenever a trunk crosses that limit. Finally, the third policy is to control the spread of the distribution by doing work whenever the second moment, or chi-square statistic, crosses a corresponding threshold. Under any of these three policies, we do achieve a steady state distribution. As you can see, we carefully chose the parameters to achieve the same steady state distribution under all three policies, but it is important to note that they do not entail the same amount of work. The conventional maintenance policy is more efficient than uniform maintenance, and the policy based on the chi-square is even more efficient. To show this in a little more detail, we now run a long-term simulation with a larger trunk group. Here we have 48 trunks in the group, and we're going to run this for approximately 3 minutes. We are using the conventional maintenance limit policy in this simulation. That is to say, if you look at the upper left-hand thermometer bar, the one in red, you'll notice that the criterion for fixing trunks is whenever a trunk goes over the limit, whenever the worst trunk in particular goes over the limit, we find and fix it and bring it back to the center of the distribution. The consequence of this is that we maintain a very precise control on the distribution of the worst trunk, and you can see that the red trace at the top of the screen is very flat. At the same time, we engender some consequential effect on the second moment, or the measure of dispersion of the distribution. And if you look at the green curve in the middle, you'll notice that we've achieved a mean steady state second moment, but we're also experiencing a certain fluctuation around that mean. The bottom red curve shows the rate at which work is being done under the policy of conventional maintenance. As you can see, it rises approximately linearly, but with some variation in timing as to when trunks are actually fixed. The yellow thermometer bar corresponds to the top of the red curve at the bottom, the work curve. As you can see from looking at the bouncing histogram, we have now contained the distribution, and we've contained it at the expense of doing work at the rate indicated by the yellow thermometer bar. Notice that the yellow thermometer bar is just now approaching the lettering underneath the green curve. Keep that in mind and use that as a comparison for the next phase when we switch policies. Notice that the steady state distribution is well approximated by a triangular distribution in the case of conventional maintenance. And notice the volatility of the green curve. Now we'll run the simulation again, but changing policies to the one based on the control of the second moment, or the chi-square statistic. That is, if you look at the white threshold on the green thermometer bar, that will be the threshold which now triggers maintenance. And as soon as that goes above the line, the worst trunk in the group will be moved back to the middle to keep that second moment from increasing. You'll now see that we are maintaining much more control over the second moment of the distribution as indicated by the middle green trace. Again, we have a steady state value, but much less variation around it. At the same time, we experience a consequential effect on the worst trunk in the group. It again has a long-term average, but it now experiences more volatility than in the earlier case. What's especially interesting in this case is that the long-term rate of doing work turns out to be considerably less than the previous policy. This simulation was carried out on a Symbolics LISP machine, and the color was added through the courtesy of the research department, which had one of these machines with color hardware. It took about 3 weeks to get the first version of the simulation up and running, and a total of about 50 hours of programming to get the version that you see in front of you here. This is a very old model known as the diffusion model, or random walk, drunkard's walk, or Wiener process model. The theory has been in the literature for at least 30 years, but is not well understood because it requires rather difficult graduate level mathematics to unfold. But the computer animated simulation makes it easy to see the main idea without having to go through a great deal of mathematical analysis. Notice that the work curve is much shallower under this policy than the previous one. In fact, we've done about 60% of the work in the previous policy to achieve the same steady state distribution.